Ska vi dra igång då?
Ja, visst.
Okay, welcome everyone. So today we have two guest lecturers here, both from Volvo Cars. We will start with Johan Lidén that some of you might recognize, since he is also involved as one of the TAs in the course, and is an industrial PhD student here working on testing. And after the break, we will have Sajid Mirimadi talking about software test strategies and how to deal with large projects. So yeah, we'll start with you, Johan.
Right.
Please.
Thank you. Okay. So, I mean, you've probably seen the title of the talk, Automatic Test Case or Test Generation of Mechatronic Systems at Volvo Cars. So that's what I will try to cover. And also, you know, you've seen me before in the first tutorial of the Crazy Fly and so on, but this is just some short background on who I am. So my name is Johan Lidén Edland, and I have a background at Chalmers. So my bachelor program was Engineering Mathematics or Teknisk Matematik, and after that I took Systems Control and Mechatronics master program. So I actually took this course, I think, 3 years ago, but now I'm a TA for it since last year. And ever since I graduated from Systems Control and Mechatronics, I've been an industrial PhD student at Volvo Cars. So what I'm working with there and my research project is how to efficiently test the models we have at propulsion energy systems. So we have models of electrified vehicles that we want to ensure that they have good software quality in them. So why do we want to test the models that we have? I've built 3 main points here. The first one is because we cannot formally verify it. So we can never be sure that the software we build in our mechatronic systems, that they are correct or that they behave exactly as we want them to behave. And this is because the models are very big and because they have continuous dynamics in them. We are also simulating plant dynamics, just like you with the Crazy Fly. And then when you get big enough or complicated enough systems, then you won't be able to formally verify them. The second one is because we want to find bugs before we actually produce the cars. Because we don't want to rely on getting to the end of the chain where we actually have a car until we can test whether or not the software we develop for it is good. If we can find bugs by testing the software virtually, then we can basically do it at the same time as we are developing new software. And then finally, which connects to the second point, this will then be cheaper than testing it in the car or testing the hardware, because you can just buy a bunch of computers and simulate a lot of them at the same time and run a lot of tests. So you can simulate and test much faster than just in real time, which would otherwise be the case if you had to sit down in a car and run the tests. So to summarize this, what we want to do is we want to have models of everything. Just like you, we want to have plant models where we have the physical behavior, and we want to have the controller or the software behaviors that we can simulate in closed loop and see if it fulfills what we want them to fulfill. So the models that we have, where me and Sajid are working, is basically 3 big models that we are testing. We're testing the electric drive, and then we have a battery system, and we also have a charger for the electric battery for electrified vehicles. So these 3 models are what we're testing. And for each model, we have a bunch of different requirements, so what we want them to fulfill. So I have a few examples of what requirements could look like. So this is one, and these are some requirements that I just came up with, so they're not actual requirements. But for example, when the car is in reverse, never allow any positive torque to be applied. So it's kind of straightforward, to the point, and makes sense. It should be fulfilled by any car. The engine speed should never reach some preset ceiling of the engine speed. Maybe makes sense in some situations, maybe it doesn't make sense in others. I don't know. Or the car is comfortable to drive, which is of course a good specification because we want it to be fulfilled, but it's not a very testable specification. It's like when you come to me during consultation hours and I ask you, what do you expect of your Crazy Fly? And you say, we want it to be stable. Then it's kind of not clear what do you want the Crazy Fly to fulfill exactly in terms of physical signals and what you simulate. Like here, the car is comfortable to drive. Well, what does that mean? And that's a problem, but that's, I mean, that's kind of what we have given here with the requirements and what we want to test. So, as you can see, the requirements are typically written in natural language, in English. But as you well know, we can be a bit more formal when it comes to requirements or specifications. So specifications and requirements, they're basically the same thing, but we usually say requirements when we have it more informal, like in English, and specifications when we have it in some more formal language, like, you know, linear temporal logic, and Knut also mentioned signal temporal logic last week for you, I think. So I think you all are kind of LTL experts, and you heard about STL, so I will not dwell too much about the details of STL. But basically, it's an extension of LTL, and we can evaluate this for simulations of data because we evaluate the specifications over real time. So this is the definition of STL here. And what it means is this mu that you have, it's that you can write predicates. So you have some signal, for example, speed or gear, and then you compare it to some value, which can also be a function of other signals, or just speed less than 50 or gear equal to 3 or whatever. Combinations and functions of different parameters and signals in your system. We can negate these, so just write not in front of them, and then you change the meaning of the specification. Logical and logical or is included in the language. And then similar to the LTL temporal operators, you have the always operator, but it's timed, so you give it an interval, A to B. So in this interval, I want this property to always be fulfilled. Timed eventually, so in a similar sense, in this interval, we want this to eventually happen. And timed until is, I mean, basically inside this interval, it's defined exactly as for LTL, but extended to real valued and real-time signals. So instead of going into too much detail here, I'll give 3 examples of STL specifications and their corresponding natural language requirements. So this first example is just an example that I came up with. So whether or not it makes sense, I mean, it kind of depends on the application, I guess. We're saying that velocity v should always be below 100. So of course, when I say always, and I'll also make it in bold here, it's quite clear that this should probably be the always operator in some way included. The proper STL specification for this looks like this here. So you have the always operator, you include the interval where you want it to be fulfilled, and the predicate here is that v is less than 100. So it's pretty straightforward. And also I think, I mean, for this kind of specification at least, quite easy to read and realize what it should mean. But it's not always the case if we have more complicated specifications. So another example is this one, which is taken from a paper about specifications for automotive systems. So I'll read here for those of you who can't see. If engine speed is always less than some preset omega, then the vehicle speed cannot exceed some preset vehicle speed v in less than t seconds. So now we have some different, 2 different predicates probably involved. The STL specification looks like this. So negate everything that's inside here. The predicates that are involved is this v that's above the limit and this omega that's below the limit. So basically what we're saying is that this v cannot, whenever this here is exceeded, then this v should not exceed its limit within this timed interval. So you have a timed interval for this predicate here, but not for this one. But already when you when you're involving several different temporal operators, like always and eventually, things can get a bit difficult to read and understand exactly what we mean with these specifications, which is kind of my point here. And to exemplify it even more, I have the third specification, which is from another paper about specifications in signal temporal logic. So, I mean, bear with me. I'll read it once more, then I'll show the specification. We'll not dive too deep into it. The point is that you can describe many things with STL, and it can be difficult to write them in a correct way if you're not trained in writing specifications. So anyways, it says, when the car shifts from gear 1 to gear 2, it should stay in gear 2 for at least tau seconds. This should hold during the entire simulations, 100 seconds. So doesn't necessarily look very complicated in natural language, I guess. But what it means is, so okay, during the whole simulation, which is during 0 to 100, then if we are in first gear, and in some epsilon time interval, where we define epsilon suitably, perhaps the sampling rate if we have a constant sampled system, then we get into gear 2. Well, that implies that between epsilon, which is the time interval that we're looking, that we're shifting up to gear 2, and then this from epsilon until tau, which is the time defined in the specification, then we should always be in gear 2. So I'll leave the specifications here. I mean, talking about specifics of STL, but I just wanted to show you some things that you can express and why it can be useful to actually define your specifications here, because then they are not ambiguous anymore. English can be ambiguous. You can phrase your requirements in different ways, but when you put them into a formal language like STL, then there's no ambiguity anymore. So what we actually use STL for in my work, or what I use it for in my research, is what we call robustness of STL specifications, which is not something I came up with. It's a research field which deals with robustness of STL specifications, basically. But the idea is that given a specification, we can not only check whether it is fulfilled or not by the system or by our simulation that we are testing, we can say how far are we from fulfilling it, or if we have fulfilled it, how robustly is it fulfilled. That's why the word robust comes in. So to exemplify this, I have a really simple example. Again, with this specification, at all times the velocity must be below 100 arbitrary unit, kilometers an hour, for example. So the specification, you've seen it before, looks as above. And then we can imagine that we have 3 different simulation traces. So each simulation is just 10 seconds long. And then you can see some velocity profiles here. We have some velocities plotted. We can imagine this is a simulation of a car. And then if I ask you which one of these, so all of them, they fulfill the specification. During all the times, all of these 3 simulations, they have velocities below 100 during all 10 seconds. But the question that I want to ask here, or that we want to know from the system, is which one of the simulations is closest to failing the specification. And so I'm not going to ask you, because it's kind of obvious here. It's this one. So by intuition, you kind of look at the highest point, which I've also marked in the velocity profiles, and then you check the difference to the velocity threshold. And then you think, okay, it makes sense that that's kind of how far away we are from falsifying the specification. So in that, if you would take that notion of robustness for the specification and the traces, then this would have robustness 50, and then 20, and then 8. And it's kind of nice because it's intuitive, it makes sense, it's easy to understand from these small examples. But it's also something that can be defined for any STL specifications using any operators, temporal operators, logical AND, logical OR, and so forth. So there are formal definitions for how should the robustness be for a given operator in STL, and then we can just recursively compute the robustness for any specification, no matter how big it is, which is kind of nice. And I'm not going to really go through all the details here, but one thing that you can notice is that the robustness, which we call rho here, which is defined for each operator in STL, if you look at the robustness for always, which is what we looked at in the previous example, here where we have that there is an always specification, then the robustness value is the minimum over a time interval of the inner specification. So you have always in some interval of phi, well, then the robustness for this is the minimum over the time interval where you're looking at of the robustness of phi instead. And then this can be recursively computed so that it makes sense according to the examples that I showed in the previous slides. So some examples here are if you have some predicates, so for example V is less than 100, then the corresponding robustness value would be 100 minus V. And on the other hand, if you have some omega that should be larger than 3200, the robustness value would be omega minus 3200. And the reason for this is that we want to map so that the robustness, instead of just giving us a logical value of either it's true or false, then the robustness value, it says that if the robustness is positive, then the specification is fulfilled. If it's negative, then it's not fulfilled. And then the magnitude of the robustness, it tells us how far away we are from failing or from passing the specification. So this is an example, again, another example for this simple spec, where you have velocity less than 100. So if you imagine this velocity here going from, basically from 50 and then up in some second degree curve and then back to 80. And I have marked in this graph where the specification is not fulfilled, where the velocity is above 100. Then the corresponding robustness value for this specification basically kind of negates it and centers it around 0. So exactly whenever the specification is broken, that is exactly when the robustness value is below 0, which is here. So that's kind of the point, because then the more negative the robustness is, the closer we are to failing the specification. And that's what we then want to do. That's kind of what we want to do in testing when we have a specification. We're looking to minimize the robustness. We want to find scenarios or counterexamples where the specifications don't hold. Because the basic assumption is that we can't check every simulation or every configuration because that would take infinite time. We can't formally verify it. So then we're trying to find examples where we see that our specifications are not fulfilled, and then we have to change our code to fix these issues or these bugs. So if we now reformulate this testing problem, or what's called the falsification problem, the research area is called falsification, then basically what we want to do is minimize this rho, which is the robustness value. And rho is a function of the specification, and then of all the signals in the system, we'll call them x, and of course the simulation time. What we then need is, of course, we need the specification stated in signal temporal logic, and we need these signals and the time, which is typically, if you just run a simulation, for example in Simulink, then you will have access to these. But then we also need something to minimize over. What do we change from each iteration to the next in this optimization problem? We'll change the input parameters k. So we have some input parameterization k, which I will come to in just a few slides. But then an overview of the problem is basically that we have our model here, and we have the k, which are the input parameters, And then given the input parameters, we can generate a trace. So we generate a simulation, and then given our specification, we can calculate the robustness value from that. And then we just iterate it, put it into an optimizer, and try to minimize the value. And then as soon as the robustness value is negative, we know that we have a counterexample. So then we have a bug that we need to fix. So all of this is done in a MATLAB toolbox, which is called Breach, which I use, which is an academically developed toolbox. So this is a more detailed image of what's going on in this falsification process. So input generator takes the input parameters. So this is where we start with some initial guess for input parameters. Can typically be random if we don't have any specific idea of what we want to test. We get an input, so then we simulate it. So this can typically be Simulink, for example, or Modelica, or whatever else. We get the output, so we get X and T. With the requirement, then the Breach toolbox takes care of evaluating this. We get an objective function value, so then whenever it's negative, we stop, and if it's not negative, we use an optimizer to loop this. So we really want to loop until we find some counterexample over at the end. So the input generator, typically, I mean, it looks like this. I will show you a few examples. What we want to do with the input generator is we want to characterize as complex signals as possible with as few parameters as possible, because we want to have a low dimensionality of the optimization problem while keeping the expressivity of the signals as high as possible. I mean, we want realistic driving scenarios, for example, for our cars, but we want to be able to represent the driving scenarios with as few numbers as possible, so then we don't have to optimize over so many dimensions. So an example is given here that, of course, we have some ranges for each signal where it makes sense that the ranges are. For example, if you give as input some torque to the motor, then it can't be infinitely high or infinitely low. There are some minimum and some maximum values that some expert engineer at Volvo can tell me what it should be. And then the idea is that we represent each input with control points. So for this input here, to get this curve, we don't need to define every point on this curve for the simulation. We just define 3 points, here, here, and here. So at the starting, at the end, and at the middle of each simulation. And then when we want this Breach toolbox to generate an input to the system for this signal, then we just tell it to interpolate in some way. I mean, we can define in what way we want it to interpolate between the points, but that's the basic idea. So with just 3 points, I can characterize a lot of different signals in a continuous setting. And it also works in a similar way for discrete signal generation. So with just 3 points, we can interpolate between them. And then after we have generated this interpolated signal, we can just floor it so that we get a final signal value that is discrete. So if we have some discrete valued signal, it works as well. So here are some examples for, I think this is an image of 20 different input trajectories generated, just using 3 control points for each. The signal range here seems to be between 320 and 500. So then you can see you can get a lot of different behavior for the signals by just using 3 numbers to characterize them, which is the point. And then it will look similar in a discrete setting, but it's more difficult to see what's going on. So here you have only 3 different possible values. So you still have a minimum and a maximum value for discrete signals, but they only change in steps, as you can see here, because they can't be anything in between the integer values. So that kind of sums up what's going on in the input generator. So we get a parameter vector k, which characterizes the input signals that we have to the system. And we simulate it, which is straightforward, using our favorite simulator. And then this is how the robustness function, this is where the robustness function comes in. But in our case, we don't have robustness functions, or in my case, I should say, the robustness functions aren't stated in STL. It's not typical that engineers know how to form specifications in STL, since it's quite a new language. It hasn't been there for very long, so it's not standard in the industry or anything. So what we instead have is we have requirement models, basically requirements expressed in a formal way, but instead in Simulink. So one of the things that I've done in my research is to parse these requirements so that the engineers can develop requirements in their own favorite setting, like Simulink, and then I can automatically translate them to STL. And then, since we have the requirements in STL, we have access to robustness calculations by this breach toolbox, and then this whole falsification loop works. So the main idea for what I've been doing with this work is that we take a requirement model which has been developed by a test engineer and can look for example like this, which is a really trivial example, but just to give you an idea. The specification here is that the signal X should always be within some preset tolerance to the reference value for the signal X. So a way that this could be implemented is in Simulink is that, okay, inside a subsystem you have imports X and X reference. Typically, I mean, X is taken then from the simulation of the system, and X reference is probably given as an input to the whole feedback system. Then you subtract the reference from X, and then you take the absolute value of that, and then you compare that to the tolerance that you have. And then this signal here, this output of this requirement model, as we call them, it's a Boolean value, which is 1 if it's fulfilled and 0 if it's not fulfilled. And then by looking at it and searching through this, basically looking at this output first and then searching backwards until we find values which have not been assigned an STL formula, then we can build up an STL formula from the ground up, you can say. So the final STL formula would be like this. You have the always operator over your simulation time, and then absolute value X minus your reference should be less than or equal to the tolerance. It's very straightforward and it's very basic and it makes sense, and this is how the STL formula would look in the toolbox itself where you write it. So far so good. This is an example of a real requirement where I have erased all the signal names and stuff because it's proprietary, but otherwise it kind of shows you that, okay, some specification, it will look kind of like this. So if you look into it, well, there's a lot of parentheses and like which parenthesis is involved in this and in this or here or in this or whatever. So it's kind of it blurs the lines of readability, but you can kind of guess what's going on in the specification if you look here for a long enough time, I guess. But then again, this is quite a spawn specification. It's a really simple one. So there can be bigger ones. And now I would say, now this is not really a readable specification anymore. This is just a wall of text. And this is still, I mean, a reasonably small requirement that has been modeled here. So the point of what I'm doing is not to gather readable STL specifications. It's to get something that's executable by the breach toolbox so that we can get robustnesses of any specification that we have that the test engineers have already implemented in a design language that they know. And it actually works out in reality, so that's neat. So that sums up this going from requirement model and into my parser, and then going into the breach toolbox so we can evaluate the robustness. And then it's just a question of what's actually going on in the parameter optimizer over here, because then we have finished the loop, and I guess you know what I'm dealing with during my days in my research. So again, I like examples, so I have another example which shows kind of how it would work. This is a curve we can say that it's the first iteration of the falsification process. So these points are generated randomly. We see that we have the control points are 11 for the start time, 8 for the middle of the simulation time, which is 5 seconds, and then 60, which is the maximum value allowed for the signal, which is in the range of 0 to 60. It has the maximum value for the last time point, which is 10 seconds. And then it has been interpolated with the MATLAB interpolation called p-chip. So from the optimizer's perspective, it doesn't really see a curve. It just sees a vector of 3 numbers, 11, 8, and 60. And we evaluate that with the objective function, which is then, some given value. It depends on the specification, of course. But then we put it into an optimizer, and we can use several different optimizers, but we don't have gradients, so we can't use any solvers that want to use gradients in the optimization problem. But anything else, like stochastic optimizers, for example, works. And then, for example, the optimizer could want to try something that's kind of close to these control points, but it wiggles around a little bit, which would generate this signal then. So from the optimizer's point of view, we just changed 3 values, from 11 to 7, from 8 to 15, and from 60 to 50. And then we get some other robustness value. And then the optimizer, depending on the algorithm, decides on getting something else. Okay, switches the value in some other way, and then given enough iterations then, and a good search algorithm, we can only hope that we will go towards lower robustness values, because what we want to find a negative one. Then we have a counterexample. So the idea is, this is given a search space, a 3-dimensional search space in this case, because we only have one signal and we have 3 control points here. So then we can have 3 points in this space, and then we generate more and more signals, like 100 or 1,000 points. And given enough points, of course, if there is a bug, then we will find it. But the main issue is to find it in a short enough time, and that's why we want to use good optimizers, find different ways to parameterize the optimization problem, change objective functions if that's possible, but those are kind of details that I will not go into right now. But that sums up my research and what I'm doing and how falsification works, and the usage of formal specifications in STL, and what robustness is and what we can use it for. So it's quite a lot, I guess. I would like to thank you for listening, and I set some time for questions, if you have any questions or comments or anything. So is there anyone who's wondering anything specific about what I talked about? Knut, how convenient that you have a question.
About how you're using this at Volvo right now.
How we're using it? Well, so really what we're doing is that, okay, so we have these models that I mentioned, the electric drive, the battery, and the charger models. And then we take them and all the requirements that I've had requirement models for, then we have an automatic script, or I have an automatic script that generates STL formulas for it. And then when we get new code, when the testers generate new requirement models, my script generates new STL formulas for it, and then we run the falsification loop on remote computers so that we can run it at all times and keep testing even though the software is continuously updated, because that's the case. We want to test it all the time to our requirements and our specifications, even when new software is being developed. and that's does that answer your question? I guess. Or was it anything specific, more specific you had in mind?
We can have let anyone ask questions.
Yeah. Is there anyone who has any question? Yeah.
The Bash toolbox, is it who owns it or who publishes it? Is it Matt?
The Breach?
The Breach.
Yeah. So Breach was developed by a professor called Alexandre Donzé, who is from France originally. He developed it when he was at Berkeley, the university in California. And it was developed, I think, 2011, I think. It was at least published. He has since left Berkeley, but is still developing the toolbox. So he's living in France right now. And he's updating it still. And we have some collaboration with him as well. Yeah, it's open source, so anyone can just download it. So if you search for Breach MATLAB Toolbox, then you can download it in a couple of minutes. So if you're interested, you can just Google for that, clone the repository, and there are some tutorials where you just basically click through it to see what the toolbox is available of doing. I mean, calculating robustness, writing specifications, running falsification, and there are also some more extensions to falsification that you can run in the toolbox, which I didn't talk about. So, yeah. Does anyone else have any question?
We have one.
All right. Yeah.
So, what I said, when you run them on simulations on remote computers, and you want keep simulating while you develop new software, but you still have to update the software, right? Or
Yeah. So I mean, what we have to do is, okay, we fetch a new, we pull the latest model that we have, then we run simulations or falsification. We run it for a while, and then we get some results that we can publish to a database that we have. And then when we're kind of finished, maybe we run it for a day or two. Then we get the newest software again. So it's like this infinite for loop or while loop, I guess, where you run falsification, you get the latest version, run falsification on the newer version, get it again. Because of course, when we find a counterexample, if we find a counterexample for software that's 4 months old, then they might have fixed it three months ago anyway. So then it's not a useful counterexample. So we need to find a scheme to run things so that it's as updated as possible when we find the counterexamples.
So do you know when you're done, or do you just run as long as you have that software, like as long as the software is
ideally we would run until we get a negative robustness value, but I mean in reality we can't really do that because of course we have limited time. The system takes a long time to simulate, and there might not even be a bug with respect to the given specification. So I mean it might never terminate. So what we need to do is, I mean, for each requirement that we falsify, set some boundary on, for example, the time that we run it or the number of robustness function evaluations we have. For practical reasons. In theory, we would just want to run. For each model, we would have one computer, one instance of MATLAB running each requirement in parallel, and just as soon as you get a new commit to your to the software, then you run falsification for the new version again and again. But then, I mean, there's limited resources and stuff. So in practice, it doesn't really work like that, but that's the ideal situation. Is it clear, or? Okay.
Can you say anything about the size of the problems you have?
Yeah. So the falsification example that I showed here, it's basically we have one input and it has 3 control points. So that would make it a 3-dimensional optimization problem. The sizes of the problems that I'm typically working with the Volvo models, we have between 50 and 100 dimensions to the optimization problem. So it's a much bigger problem, much harder problem to solve, and the simulations also take a lot of time. A simulation could take 1 minute, for example. And then you really need quite a few iterations of this falsification loop to get something useful from these stochastic optimization solvers. So it's, I mean, it's a built-in challenge in these models that they are very big. They have a lot of input, a lot of parameters to change, and that's why we need a lot of resources to solve the testing problems.
So, and what are the open problems here? If you've got students doing a design project or a master thesis, what do you think is here to solve?
Yeah. So if we take the so we can talk specifically about the falsification process. Then there are a number of problems. I think the most interesting ones in which we are working with as well is the robustness function. So the definition that I gave before of STL robustness, maybe we can define it in some other way to make it easier for these stochastic optimization solvers to converge in a more quick way towards the best solution, I mean the minimum robustness value. So we're looking at how can we reformulate it, the robustness value for different STL operators. That's one problem, I guess. I mean, another problem that has been researched a lot specifically by one research group in Arizona in the US is what kind of optimizers work well in this falsification setting for specific types of models. So I haven't really done too much work in that field, but the result of that is that there are a lot of optimization solvers that are available to me for me to use in my problems. So that's nice. But I think there's always progress to be made in optimizers for specific applications. You can never make an optimizer that is perfect for every application, I guess. So that's an interesting problem. And then, of course, I mean, what I've been working with here, this is not finished work. I guess, I mean, there's always something that you can build upon and take in more classes of requirements that you can write here and parse in a good way. And then for each signal temporal logic formula that you want to evaluate in breach, you have different parameters you can set, evaluating what would be the best parameter values to use for different types of specifications would also be interesting. So I would say there are several problems just inside this falsification perspective, and then inside the testing perspective there are a lot more problems to solve. And then connected to that is verification, which is also a huge area. So the researchers dealing with formal verification, they are all the time working towards being able to verify more complex system, where you have, I mean, hybrid dynamics in your systems, and so there are formal verification tools for specific types of hybrid systems that you can actually verify. But they're kind of limited and wouldn't at all work at these sizes of models that we have at Volvo. But it's still an interesting, I mean, of course, an interesting problem to work on. It's just, I would say they're very far away from having some verification tool that runs in reasonable time on industrial size model like the ones that we have.
Are you allowed to say something about how many bugs how hard is it to find bugs and when do you find them and so forth?
I think Sajid will talk a little bit about more details. Maybe give some example at least.
Okay.
Yeah. Yeah. So the general answer is that it's very hard to find bugs in software. When it's developed by hundreds of engineers, it's very difficult to find like where there is a bug. And I mean, typically, no matter how much testing we do when we develop a car, I mean, when you release the car, then within a month, the consumers will have driven 1,000 times more than we can ever drive in testing and simulation anyways, because there are so many drivers driving the cars. So if there is some bug which has a very small probability of being found, then, I mean, we really need smart testing methods to find the bugs, since otherwise the drivers will find the bugs, and it can be very critical.
I'll talk a bit more about it.
Okay.
Yeah.
Okay, so let's give Johan an applause.